My apologies. So if you can hear me and you can see my screen, we can begin. Again, please give me a thumbs up. I had one issue which I needed to resolve. If you can see my screen, give me a thumbs up. So plenty of thumbs ups here. We can get done and work on this question. So I see hands up. If you have a hands up, please shoot. But let's get to the question and see exactly what is this problem, because I've been seeing it in groups popping up, and I've been getting it from people in their personal capacity. So let's quickly go straight to the problem and see. So one thing you should do is you cannot go into the exam not knowing how to do such a question. So let's confirm our recording is up. Yes, it is. So we can go straight to the problem. So if I zoom in here, they are saying, this is the last part of algebra, if you remember. So they're saying use diagonalization. So let me highlight this term here. They're saying use diagonalization to find the trajectories in the vector field below. So let's quickly see what you are supposed to do when you are faced with such a question. So the first thing you should be able to do is, if you remember when we are dealing with diagonalization, the center diagonalization, what we are always busy about, was A, or matrix A. It's always there. So now what we need to do is we need to find the matrix A from this vector. Then afterwards, we do the standard processes. We need to find the eigenvalue and then find the eigenvector, find the T matrix, then find our diagonal matrix. So when we look at V, the question we should be asking is, what is A from V? So if you can look at these expressions or this V, let me write it this way so that you can be able to extract what your A is, and then we can start working. So your V is in the form of X, Y, and Z. So meaning we have an X component, a Y component, and a Z component. So if you look at the X component, which is just this here, which corresponds to that, then the Y component is that, which corresponds to that, and the Z component is that last part, which corresponds to that one. So if you look carefully, what's going to happen is the X component will be negative X minus Y plus Z. The Y component will be X minus 2Z, and then the Z component will be Y plus 2Z. So one of the ways, or one of the easiest ways we can separate this matrix is by splitting it into the X's and the Y's, and then we take those rows. So if you look at what is going on here, I can write this matrix as I have my negative X, I have my X, and then here I have 0x. That's why I don't see any X. So I can put a 0. Plus, then I can look at my Y's. So for my Y's, for the X part, I have negative Y. So I'm going to put negative Y there. And then for the Z part, I don't see any Y part, which means it was 0. And then for the Z part, I see a Y there. So it is there. Then we close the bracket. Plus, so let's focus on the Z's now. Where is green? So if you look here, for the X part, we do have a Z. So we'll put the Z here. For the Y part, we do have negative 2Z. So we put minus 2Z there. For the Z part, we do have a Z, which is 2Z. And then you close your brackets there. So what you can do from here is you can see that from these matrices, this is still the same matrix as the one you have. You can factor out your X from the first one, and then we have negative 1, 1, and 0. then plus y. You can factor out your y, you'll have negative 1, 0, and 1. You can factor out your z on the last one, and then you will have your 1, negative 2, and 2. So our A matrix will be what we see here, these ones, will be the columns of our A matrix. Because remember, we said before we even stress about diagonalization, we always need to find matrix A, because the center of diagonalization is around matrix A. So all what we took the V, wrote it in this form, separated the X's, the Y's, and the Z's, and then these columns which you see here are going to form the columns of matrix A. So therefore, our matrix A is going to be, first row is negative 1, 1, and 0. Second row is negative 1, 0, and 1. Third row is 1, negative 1, negative 2, and 2. And this is what we call our matrix A. So after finding A, life becomes very easy, because once they speak about diagonalizing, you find your A, usually you are given in other problems. After finding your A, you now need to find your characteristic polynomial. After finding that, you find your eigenvalue. After finding those, you find the eigenvector. After finding those, you find the T matrix, then the D matrix we are now going to have. And then from there, it is as easy as D operators. So now that we have our A, we need to follow a series of steps. So after finding our A, step number 1, so usually you'll be given, but us, we have to find A. After finding the A, step number 1, you must find the characteristic polynomial. Characteristic polynomial. And all what that is CA lambda is equal to the determinant of A minus lambda times the identity matrix. So if you've seen in past papers, they are always saying, what is the characteristic polynomial? So you can't go in the exam not knowing how to find your characteristic polynomial. Okay, so we have our A already. So let's copy and paste our A here. So there's our A, and then I'll put the straight line here, which is for determinant. Then we need to minus by, since A is a 3 by 3 matrix, our identity matrix will also be a 3 by 3. So we'll have lambda here, 0, 0, 0 lambda, 0, and then 0, 0 lambda, and then we put our straight line, which is just for determinant. And this is our CA lambda. So let's quickly try to simplify that. So our CA lambda becomes the determinant of. So if you look carefully, we'll have 1 minusing that, and then we will have also the term minusing that one, and the term minusing that. So if we do exactly that, what we obtain is negative 1 minus lambda, negative 1, 1, and then we have 1. 0 minus lambda becomes negative lambda, and then we have negative 2, and then we have 0, 0. Let me push this to the side a bit. And then now what we have is 2 minus lambda, which will be 2 minus lambda. So all what is left now for us is to find the determinant. Missing a 1 here. Supposed to be a 1. Let's check. Yes. Okay. So now we are supposed to find our determinant. And for those who recall, I said your determinant, you always choose the row or column with many zeros. So let me say here, choose the row or column with many zeros. And the reason for this is because it makes finding the determinant to be easy. If you have the row with many zeros or column with many zeros, finding your determinant makes it to be very easy. So before you find your determinant, you should remember you need what we refer to as the sign matrix. And the sign matrix, all what it is a plus, minus, plus, minus, plus, a minus, a plus, a minus, and a plus. So whenever you're doing this section of diagonalization, you need to have your sign matrix. If you do not have it, there's something which is wrong with you are doing. Okay. So with this set, we have our sign matrix, and then we have our matrix there, which we want the determinant of. So looking at what is going on, I'm going to choose row 3 as my row, because row 3 is the one which has many zeros. Many zeros can be 1 sometimes. It can be 2 if you are lucky, but many zeros here is 1. So I'm going to choose row 3. I'm going to choose row 3 as the matrix or as the row which I'm going to perform the operations on. So let's quickly copy this, go to the next page, and start doing our operations and see if we can find our characteristic polynomial. So let's quickly add pages here. Hopefully that's going to be enough. So let's paste what we had. Okay, so if I use row 3, if you look carefully, I have 0. So how I'm going to operate is in this way. I'm going to be operating on row 3, but I'm traversing on the columns. So I'm going to start on column 1. So if you see where there's a cross, it's a 0, but I need to put a plus there because of my sign matrix. So I need to put a plus 0. And then what is left is what I'm going to take the determinant of. So if you look at what is left is negative 1, 1, this and this. So what is left inside is negative 1, 1, negative lambda, and minus 2. Okay, now I traverse to the second column. I draw a line like this. And then I can see on the second column, I'm crossing a 1 there. But my sign matrix is saying I need a negative. So I'm going to put negative 1, put the determinant of what is left, which is negative 1 minus lambda, 1, 1, and minus 2. Okay, now we need to go to the third column, and then we are good as done. So let's go and scratch the third column. And my sign matrix is saying on the third column, this element here should have a plus. So I'm going to put a plus there. Let's put a plus, and then what are we crossing? We are crossing 2 minus lambda. What is left inside? It is negative 1 minus lambda, negative 1, and then 1 minus lambda. So now I need to find the determinant of these. And if you recall, finding the determinant of a 2 by 2 matrix is extremely easy, very easy. So let's copy this to the next page and find these determinants. And guess what? That is going to be our characteristic polynomial, which in the exam you will need to find before you get your eigenvalues and eigenvectors. So for this one will obviously be 0 because whatever we get outside there will multiply by 0, which is why I was saying in finding your determinant, choose the row or column with many zeros. Okay, so that's why I said choose the row or column with many zeros because it makes your life to be easy, as you can see right here, that my life is easy because that has just become a 0. So let's find the determinant for the other ones which are left. So remember that this is still equal to CA lambda, which is our characteristic polynomial. So we have -1 multiplied by the determinant of a 2 by 2 matrix. If you remember, you take this term which is here, you multiply it with that term, and then you take the term which is here, you multiply it with that term, but then you put a negative in between when you multiply in that direction. Can you see my screen?
Yes.
Okay. No problem. Let me carry on. Can you see what I wrote in purple, those circles?
Yes.
Okay, so if you can see purple circles, then let's carry on. If you can't, please inform me. Okay. So if you're looking for a 2 by 2, the determinant of a 2 by 2 matrix, that is, let me open the bracket. So you'll multiply -1 minus lambda with -2, and then you will subtract 1 multiplied by 1. And then when we look at the other determinant for the plus 2 minus lambda, we will cross multiply as we did with the previous one. You multiply these ones, and then you look at the purple ones. You multiply them, but you multiply, when you multiply, you put a negative after them or before them. So for that second part, we will have -1 minus lambda times negative lambda, then minus 1 multiplied by -1. Okay, so let's quickly FOIL and then factorize that expression and then see what we can obtain is our characteristic equation. So our CA lambda will be equal to, I have -1, open that bracket, what we will have is 2 plus 2 lambda, and then minus 1. And then we are closing that bracket. And then plus 2 minus lambda, open bracket. What we have inside there is simply lambda squared plus lambda plus 1. Okay. And then if you look carefully, all what we are going to have now is after distributing the negative, you will have, let's see, -1. And that's so 2 minus 1. Let me put the -1 there. It's going to be 1. And then plus 2 lambda. And then I have 2 minus lambda here. And then lambda squared plus lambda plus 1. Did we not make any mistake anywhere? So please make sure you double check my work. With these kind of questions, making a mistake is extremely easy. It is very easy, and once you make a mistake, it will catch up with you later. So let's quickly see if we made no mistake anywhere. So let me look at the last part. So that's 1 and the -1. And then the second last, it's a 1 and a 1. Okay. So is there anyone who sees a mistake which we might have made here? It's in a class here.
Okay.
Yes.
Why are you multiplying everything? Yeah.
Can you repeat your question?
I say I can see you are multiplying all the brackets. I don't understand why.
Okay, can you see the modification I made now?
Yes.
Can you see that I separated them?
No, I don't see it.
Okay, what can you see on my screen now? Looks like I have serious network problems here.
C minus 1 bracket x plus 2 lambda bracket 2 minus lambda bracket
Okay,
lambda squared plus lambda plus 1.
I see what you see because I made a modification now. There's a plus, but it looks like my network lag is really horrible. So load sharing is working together with other people who do not want to pass to make sure that we do not move successfully in this session. So I made a modification now. I don't know why it's not working. So now it is ESCOM working with people who want you not to pass, who are really screwing us up. I'm telling you, because I made a modification now. So it's either the network lag is really bad.
Yeah, it's okay now.
Yes. So please today make sure you all pray because ESCOM wants you to fail. So you should go and post there and say, you know what, ESCOM is affecting us. We're in a session. I want to see, but there's a lag. So ESCOM wants the edge to take you down. So let's quickly have a review before we carry on if we made any mistake anywhere. Because what I've seen from experience with these problems, you make one mistake somewhere, you are screwed. Okay, so let me go back to the vector we're given and we quickly have a look if we didn't make any mistake. So let's zoom in. Let me see. This should slide. Okay, yes, same page. So let's quickly zoom in to the vector and see if we made no mistake anyway. And then we progress and then we eventually get that side. So that's one thing you should always try to avoid. If you make one mistake with these problems, it really it catches up later because you'll have difficulties factorizing. So let's quickly see. So the first row should have a coefficient, which is -1. There it is. Let me use different colors here. So we have -1, there it is. We have another negative, there it is. And then we should have a +1 there it is. So that's okay. No mistake in our A matrix. And then now let's look at the second row. So for the X, we have a coefficient, which is 1. There it is. For the Y, since we don't see it, we have a coefficient of 0. There it is. For the Z, we have a coefficient, which is -2. So we are set. Then let's check the last one. So for X, since we don't see it, we have a coefficient of 0. That's okay. For Y, it's a coefficient of 1. For Z, it's a coefficient of 2. So no mistake here. So let's go to, let me wait a sec. Okay, can you all see my yellow ticks? So please be patient. ESCOM is to blame. So if you can see my yellow ticks, give me a thumbs up. Okay, great. So let's see the next page. So for this, you'll really need to be patient. There's someone to blame. We blame ESCOM, the minister who's dancing. So let's quickly look at the other side. So if we did our matrix A correct, let's quickly see if we did our subtraction correct. So we said our characteristic polynomial is given by, it is given by the determinant of A minus lambda times the identity matrix. So be there with me. So let's see if we did the subtraction correct. So we have -1 in that, so this is correct. And then for the middle term, we have 0 minus lambda, which should also be correct. And then also, if you look at the last term, we should have 2 minus lambda, which should also be correct. So please look carefully and then be patient. So that step is also okay. We did not make any mistake there. Okay, and then if you look at what I wrote in green, I said, when you do your determinant, choose the rows or the row or the column with many zeros. The reason is because it makes your life to be very easy when you compute your determinant. Okay, so which means if you look at my matrix, the one or the row or the column with many zeros is obviously, I'm going to choose row 3. Many zeros, as I said before, it can be even 1 0. If you get 2 zeros, you are very lucky. So we'll choose column 3 as the column which has, or as the row, we'll choose column row 3 as the row with many zeros. Then what you need to remember is the sign matrix. You cannot afford to forget the sign matrix. I wrote it here. So let's go to the next page and see if we still have the same steps. Okay, so this page here, let's wait, it's gonna scroll. So let's see the next page. It should be up now. So if you look at this page here, let me erase that blue line and take it to the front, and we'll see how we obtained that first determinant after the line choose row 3. Okay, so if you look at that and you look at our sign matrix, where there's a cross between the purple and the blue line, we have a 0 there. So that's why below we have +0 there. And then what is left inside is -1, 1, and then negative lambda and -2. That's why we have them inside here. So that should be clear. And then let's quickly look at when we traverse over the columns. Let's go to column 2. So when we go to column 2, what we are crossing is a 1. And there's the 1. The negative here comes from my sign matrix. That's where the negative is coming from. And then if you look at what is left inside, after crossing, it is what we have there. So we have -1 minus lambda, -1 minus lambda there. And then we have +1, and then we have +1 there, and then we have a 1, and then we have a 1, we have a -2, and a -2. So we didn't do any mistake there. And then let's traverse now and go to row 3, or column 3, sorry. Let's go to column 3 and see what is going on there. So if you look at column 3, what we are crossing, where there's the blue and the purple line, it is the 2 minus lambda. And then after crossing that, if you look at what is left inside, it is -1 minus lambda, which is what we have, -1, which is what we have, a 1, which is what we have, and then negative lambda, which is what we have. Okay. So what we now need to do is to find the determinant of these. So let's look at the page, which is just following that one. I'll zoom in a bit and we can conclude this problem, find the factors. Okay. So if you look at the matrix where I cancel with the green and I said it is 0, it's because we are multiplying that determinant by 0, which is why I said choose the row or the column with many zeros, because you can have this privilege and cancel things out without doing any work. So you need to be lazy smart. Sometimes hard work doesn't pay off. Smart work does. And the other way around can be true, depending on the situation. Okay. So we clear that with a 0, and then what we are left with is a 2 by 2 determinant. So if you look at what is going on, the 0 determinant is gone, and then we have the 1, which has -1 at the front. Then all what we do, as I highlighted, we multiply those. I hope that's yellow or orange, whatever it is, we multiply those, and then we multiply the purple ones, but we take the minus sign when we multiply those ones. Okay, and what we obtain is the expression we have here. And then for the 2 plus lambda, we do the same. Multiply those, and then you take the minus, and then there you go. That's what you have. So now what we need to do is to do the foiling, obviously, which is what I was running away from. But let's do our foiling and see what we obtain. Okay, so I was just checking if we made no mistake, because once you make a mistake, it catches up later, and usually most of the time, when it catches up that time, it's a bit too late to rectify some of these mistakes. Okay, so if you multiply this one, you get -1 minus 2 lambda. And then if we deal with the bracket, you will see it shortly, we'll have 2 lambda squared plus 2 lambda plus 2. And then if you multiply the lambda in, you have negative lambda cubed minus lambda squared, and then minus lambda. And this is, if you remember, this is our CA lambda. Then our CA lambda, if we finalize this, it will be our negative lambda cubed. And then let me group the lambda squared terms. Let me see, we have this one and that one. So which makes it to be plus lambda squared. And then let me look at the lambda terms. So we have -2, +2, and -1. -2, +2, and -1. That should give me -1. So that's negative lambda. And then if you look at the constant terms, we have -1 and +2. So that should be 2 minus 1, which is +1. See, 2 minus 1, that's +1. We have another constant term. The answer is no. Okay, so this is our characteristic polynomial. So if they say find the characteristic polynomial, the lecturer will be happy when you are here. Characteristic poly. So when you get here, the lecturer will be already very happy with you. You will see the characteristic polynomial shortly. Be patient. We should blame ESCOM here. It's interfering with our exam prep and academics. Okay, so if the lecturer was saying find the characteristic polynomial, they would be happy if you give them such. So now after finding the characteristic polynomial, we now need to go and find what we refer to as eigenvalues. So let's go to the next page and find our eigenvalues. So here we need to find our eigenvalues. What are they? So what you usually do with these problems is you need to find a factor. After finding one factor, it's easy to find the other factors. So this here, if you look carefully, we can easily find the factors. We did this back in grade 9, imagine. So let's see. So if you look at how we could find, or how we can find the factors here, you can factor lambda squared from the first part and then have negative lambda plus 1. Then factor a positive 1 from the second part and then have negative lambda plus 1. And if you look carefully, we now have another factor, a common factor, which is negative lambda plus 1. So we can just factor out negative lambda plus 1, CA lambda. We'll have negative lambda plus 1, and then inside the bracket, you'll be left with lambda squared plus 1. So now finding your factors is very easy. And your factors, they are your eigenvalues. So if you remember, negative lambda plus 1, when you find the factors of lambda squared plus 1, it is just lambda minus I, then lambda plus I. Okay, so now when we're looking for our evals, I'm just going to say it is eval. We just equate these to 0. So negative lambda plus 1, we equate it to 0, and then the same goes for lambda minus I, we equate it to 0, lambda plus I, we equate it to 0. So our lambda will be positive 1, another one will be I, the other lambda will be negative I. So now we have our eigenvalues. Now what is left of us is to find the eigenvectors, and then afterwards, this thing just becomes easy and you are good as done. So for getting here, you would have obtained plenty of marks for your ability to find your eigenvalues, the evals. So let's quickly look at the EVEX eigenvectors. So for you to find your EVEC, you take the matrix which we had before we found the determinant. So remember that every eigenvalue must have a corresponding eigenvector. So let's quickly take the matrix we had before we started doing or finding the determinant, which is that matrix there. Let's copy it, go with it to the next page, and paste it here. You'll see now what I was copying and pasting. Can you guys hear me? Okay, no problem. Can you also see my screen? You know, it's painful, but this is the country we live in and ESCOM is happening. But anyway, we need to make the best of the situation. So if I could fix ESCOM, I could. But anyway, let's carry on. So my network is really not good. Hey, wait a sec, you'll see what I wrote there. So immediately when you can see a matrix with slashes and zeros on the other side, please inform me. Just give me a thumbs up. Okay, do you yet see the full matrix which has zeros on the right-hand side? No. Okay, so let's give it some time.
Hi, sir.
Yes, let me stop sharing and then try sharing again. Yes,
Okay,
you can shoot.
I didn't see your screen. That's the problem. I didn't see your screen.
Okay, let's say stop sharing and then try again. It's now when they say this thing of electricity is killing even the economy, if you can see it screwing up academics, then clearly we have a problem. So you should be able to see that matrix now. So give me a thumbs up if you can see it. Okay, great. So let's carry on here. So this is the matrix which you need to take for you to find your evals or evects, eigenvectors. So let's start by finding the eigenvector corresponding to lambda 1. Lambda is equal to 1. So we are finding the eigenvector corresponding to eigenvalue 1. So all what we'll do is where we see lambda, we'll put in 1. That's all what we will do. So let's take that matrix, and then where we see lambda, we put in 1. So the first part will be -2. We'll maintain -1 there, the 1. And then the zeros will still be there on the right-hand side. And then second row, the index will be 1 minus 1, and then -2. Third row will have 0, 1, and then 1, and then we close that. So remember that what we are trying to do here is to have as many zeros as we can on the columns. So one of the easy ways you can work around this one in case you are avoiding doing Gaussian, what you call elimination. I'm just going to take the expressions row by row. So this is row 3. And then that one is row 2, obviously, let's say R2. And that one is R1. So what I can do easily, let's look at row 3, because it is a 0. So it makes our life to be easy. So row 3, the expression is 0x plus 0y plus 0z is 0. No, sorry. The coefficients there are 0x plus 1y plus 1z. This should give us 0. So if you can look carefully, you can conclude here that y is equal to -z. That's row 3. So let's go to row 2, doing this. Let's go to R2. So row 2, the expression is 1x minus y minus 2z should be 0. But we already know that we can write y in terms of z. So this expression becomes x minus our y, we know it is -z, minus 2z equals 0. So your x will become your 2z minus z, which will be z. Or let me rather do it right here so that we have no confusion. So your x will be x plus z minus 2z equals 0. And this, if you look carefully, it will be x minus z equaling 0. So therefore, your x is equal to your z. Okay, so with this here, we are good as done as finding the eigenvector. So see what's going on. The G there. So look at what is going on here. So our evec, let me call it evec 1. Your eigenvector, you know, it should be of the form x, y, and z. And then your x here, you obtained in terms of z. So your x is z. And then your y, you obtained as -z. So we put -z here. And z, we know it is equal to z. So you can put the z here, vector out the z, and have 1, -1, and 1. And then the easiest z value you can choose z is 1. Okay, so after choosing z is 1, our eigenvector is, let's make some space, we'll call it evec 1. So our evec 1 is now 1 - 1, 1. And this is corresponding to eval eigenvector 1, which is 1. So that's how you find your eigenvector. So let's do the same for the eigenvector lambda is I. So let me copy the matrix above, and then I'll just put I where I see lambda. Let's go. Okay, so where we see I now, where we see 1, we are gonna put I, or where we see lambda. So let's go and do exactly that. So we are gonna have -1 minus I, and then -1, 1, put your zeros. And then the second row is gonna be 1, and then minus I, and then -2. Third row is gonna be 0, 1, 2 minus I. So now we can do exactly the same thing. Okay, so look, I'm gonna start on row 3. So I have my row 3 here, my R2 here, my R1 there. So let's start with row 3. So all what row 3 is saying is, if we do 0x plus 1y plus 2 minus iz, we should get 0. So this means that my y will be -2 minus I times z when you transpose. Or in other words, my y will simply be I minus 2 times z. I just multiply the negative in. And then now with this, we go to row 2. Row 2 says 1x minus iy minus 2z should give me 0. But we know we can write y in terms of z, so why not? So we will have x minus I into my y is equal to I minus 2 times z, and then minus that 2z there. This should be 0. So we quickly multiply the negative I in. So you will have x, negative I times positive I. Let me say plus negative I times positive I, it is positive 1. And then negative I times -2, it will be plus 2i, and then z minus 2z is 0. So I can group the z's here and have, that will be 1 minus 2, which will be -1 plus 2i times z will be 0. So I can transpose now and write x in terms of z. So my x will be -1 plus 2i times z. If you distribute the negative in, all what you'll have is simply +1 minus 2i times z. And just like what we did before, you now have your y in terms of z and your x in terms of z. You can now write your evec. So my evec 2, or your evec 2, you should know it takes the form of x, y, and z. And if you look carefully, my x here is 1 minus 2i times z. My y we obtained as I minus 2 times z, and then my z is equal to z, obviously. And guess what? We can always factor out the z and be left with 1 minus 2i, and then I minus 2, and then 1 here. Then just like before, choose a Z value. Choose Z is 1, the easiest. And then your E vec 2 becomes. So finally, your E vec 2 becomes 1 minus 2i, I minus 2, and then 1. And the corresponding eigenvalue, which I'm going to call eval 2, which we used to find this, is I. And then now this is why I was saying sometimes working hard is actually hard. So you need to work smart. We have an eval, which is I. Now we want to find the corresponding evec value for an eval 3, which is negative I. So now what we needed to find here was evec 3. But however, we know that eval 3 is negative I. And guess what? When you look at I and negative I, these are conjugates of one another. So if the eigenvalues are conjugates of one another, then the eigenvectors are also conjugates of one another. So let me write that as a note for you, and then we conclude this. If the eigenvalues are conjugates, then the corresponding eigenvectors are also conjugates. So instead of doing the same tiring process, what I did here was what we call working smart. So I already have the eigenvector corresponding to I. Now I'm looking for the one corresponding to negative I. Guess what? I just need to take the conjugate of the eigenvector number 2. So which means eval or evec 2. No, I'm looking for evec 3. Will be the conjugate of evec 2. And the answer is why. The reason is because eval 3 is the conjugate of eval 2. This is there because. So, which means this in summary, our evec number 3 will be the conjugate of 1 minus 2i is 1 plus 2i. Conjugate of I minus 2 is negative I minus 2. Conjugate of 1, that's real, it becomes 1. Okay, then now we are good as done here. And then guess what? After finding all the evecs, we need to find what we call T, the invertible matrix.
Sihle,
Yes.
can I ask, this method you just showed us, then I want to understand, does it only hold for when the entries in the matrix are all real, or does it also hold when the entries in the matrix are also complex numbers?
So this would hold if these entries are only real. So I think the one where you will have complex entries, that's for you second semester people. So I think first semester people can have a breathe in. But then in case the lecturer decides to say, you know what, we are not in good terms, then you would need to go the hard way. But for first semester people, I think it's chilled. They will give them real entries so they can get away with doing this. Does it answer the question?
Okay, thank you.
Yes. Okay, so now after finding our evecs, we need to find what they call, you'll see there in that exam, they will say invertible matrix. Invertible. This is wrong, forgive me. I need a tutor. Invertible matrix. So if they say such, all what they are saying, there's a matrix T, which they call invertible. So that's the matrix which we are trying to find here. And T, all what it is your T is made up of the columns of T. The columns of T are the eigenvectors. So this is that easy. After finding your eigenvectors, all what you need to do to get your invertible matrix, which is T, take those eigenvectors and then make them the columns. And there you go, you are done with your T. So my T is gonna be T. My T is gonna be, I'm gonna go and fetch one of the eigenvectors and make it a column. So let me take the very first one. The eigenvector we obtained was this one. So let me copy that. Copy it. And then I come and I paste that eigenvector. I make it a column. I go and take the other eigenvector. It's a 3 by 3 matrix. I need 3 of them. I take the other one. I'm also gonna make it a column. That's the rule. So we make it a column also. Then now we need the last one. And also it is gonna be a column. Let's make it big. And there you go. That's your T matrix. So if you look carefully, this is evec 1. And then if you look carefully here, this is evec 3. And then if you look carefully, this one here is the column that is evec 2. So after finding these, life becomes easy because now I have my T matrix. All what I did, the columns, I made them to be the eigenvectors. So I know even eval 1. So corresponding to evec 1, I have eval 1, and eval 1 was 1. And then I have eval 3 corresponding to evec 3. Eval 3 was negative I. And then I have eval 2 corresponding to that, which was I. So now I have my T matrix. I can now find the D matrix, which is the point of view doing all this diagonal matrix. So let's copy that and paste it here. And you see how we find the D matrix, which is very easy. No one has a reason why they should get it wrong. Oh, you don't belong there. Okay, cool. So now what we need to find is our D. Okay, so if you look at our D, all what it is it's gonna have our D should have zeros everywhere besides the diagonal. So it's only in the diagonal that we are not expecting any zeros. But otherwise, everywhere else, we have zeros. Okay, it's only the diagonal that we expect numbers. And guess what? The diagonal should have eigenvalues. That's what should be there. But then how you decide which eigenvalue sits where is by using the T matrix. So if on the T matrix, my column 1 is made up of evec 1, then here I should have eval 1, which is 1. And then when I look again, the second column was made up of evec 3. The corresponding eigenvalue should be what sits there, which is negative I. And then equally so for the last one. The eigenvalue, which should sit here, is the one corresponding to the eigenvector occupying row or column 3. So which means there I need to have my I here. So all what you do for you to get your D, you use your T matrix. You are saying, okay, which eigenvector occupies column 1? And what is the eigenvalue which corresponds to that eigenvector? And then you just put it there. So that's how you get that done. So there's a lag. Let me quickly stop sharing and then share again, and you'll see what's going on. Give me a second. Let's stop sharing and then let's share again. So you should be able to see all what I was writing here. Give it a sec to pop up. Can you all see my screen? Please confirm. What can you see on my screen? Can you see the finished D matrix? You can give me a thumbs up.
Yes.
Okay, no problem. So if you can see the finished D matrix, then we are good to go. So now that we have our D matrix, we can easily solve for our trajectory. Okay, and let's copy this D matrix. I'm happy with the thumbs up. Let's copy the D matrix and see how you can solve for your trajectory from here. So how you solve for your trajectory, we think along the lines of D operators. Okay, so all what you do is you will have your X dot here, and then you'll have your Y dot, and then your Z dot. After finding your D, then all what this is equal to, you put the D. So you have 1, 0, 0, 0 minus I, 0, and then 0, 0, I. And then this side, you are going to have your X, Y, and your Z. So if you multiply these matrices, all what you'll face at the end is that this one will multiply with that. That's the only significant part for that. This one will multiply with that. Everything else will be 0 for that row. And then this one will multiply with that. So the equations here will end up being X dot equaling 1 times X, and then Y dot equaling negative I times Y, and then Z dot equaling I times Z. Because you are trying to solve for your trajectory, you want the expression for X, for Y, and for Z. So if you look at what is going on here, you can transpose and have your X dot minus your X equaling 0. Then you can have your Y dot minus, that's going to be plus IY equaling 0. And then you can have your Z dot minus IZ equaling 0. Okay, so if you look carefully, here all what we have is D minus 1 times X equaling 0. And then you have Y plus I. No, it is D plus I, sorry. D plus I times Y equaling 0. And then you will have your Z or your D minus I times Z equaling 0. Can you all see my expressions? Okay, I see thumbs up, so we can see my expressions. So let's copy them to the next page and conclude our trajectory. Okay, so now what we see here is that you can solve for D. So your D will be 1 for that case. And then your D will be negative I for that one. And then your D will be I for that one. So that means our x, we write it in different colors. So that means our x will be ae to the 1t. That's the root. And then our y will be be to the negative it. We'll come back to this one. And then our z will be ce to the it. And guess what? This is what they would be expecting you to find when they speak about trajectories. And to wrap up the solution, what you can do is you can leave your x dot as so here you are supposed to have your x, which is ae to the t, your y, which is be to the negative it, your z, which is ce to the it. And then the matrix which comes here, your final solution is the T matrix. And there you go. So if you see these kind of solutions, they are really easy to work around. So this is how you would present your solution, and this would be their trajectory which they are looking for. Do you have any questions here?
So I just wanted to ask, the applications of diagonalization in different equations, have you done at least one example on that?
Yes, so all what you do is with different equations, you do exactly what we did here. Let me see if I can think of something on top of my head. I'm trying to think of a different equation. Give me a second. Okay, let me come here. So all what we are supposed to do with these problems fundamentally, you need to be able to extract the A matrix. And then afterwards, you accuracy done. So in fact, there's a difference equation or difference equation which I solved using diagonalization. I think the solution should be floating in the groups. So depending on which group you are, if you go to gallery, you can easily find it. If I remember, I'm not gonna do it now. So if I remember, I think it was, Bn minus, let me make it Bn plus 1 here, minus, let me say 5/2 here, Bn, and then let me say minus, this should be minus Bn minus 1, and then I forgot this what it was equal to. I really don't remember. So I think you should check in the groups because I'm trying to recall this and it's screwing me up. There's a solution which I did on different equations. But the point is to always make sure you can extract your A. By getting your A, things become very, very, very easy. So what you should do, let me quickly recap here, and then we can call it a rep. So if you happen to come across a equation which is a vector like this, we do not panic. The first thing you do is you write the vector in terms of its x component, its y component, and its z. And then you extract the coefficients. And then you are able to compile your matrix A, those coefficients. Then afterwards, characteristic polynomial. You find the determinant of A minus lambda in. And then you do all the work. And then until you come across or you find your final characteristic polynomial expression. And after having that, now your stress is factorizing. Factorize those, equate them to 0, and then solve for your evals, which are your eigenvalues. There you go, we found them. Then afterwards, you can start stressing about finding the EVEX, eigenvectors, and then if you are lucky enough, if you find that you have a eigenvector value, which is a conjugate of another one, you can easily get away what I said, you can do this side and carry on as we did. Compile your T matrix, which is nothing deep. The columns should be your eigenvectors. And then finding your D matrix, you just question yourself. The row 1 or column 1 of T, it corresponds to which eigenvalue. And then you take that eigenvalue, you put it as column 1 of D. But anything below should be zeros. And then you do the same for the all rows, and then until you come here, and then you conclude the problem. So do we have any questions on this problem here?
So
or anyone?
Can you be
Yes.
able to share a document on WhatsApp, the PDF document of this problem?
You mean the question or this?
The method, the way you did things. Can you share this document on the WhatsApp group, or can you screenshot the pages?
Yes, I can for sure share the solution to this problem. And then what I needed you to take away is just be careful. Diagonalization is going to be there in the exam, and you can't go there not being comfortable with such. So make sure from now until tomorrow, you go and look at diagonalization problems, because when I saw them, they carry about, some of them, as much as 20 marks. Because what we did here, they would ask you step by step. The first thing, maybe they would say, find A. They would say, find A. And then for A, for weird reasons, they give you 3 marks. Imagine. And then they say, find the characteristic polynomial. And then they say, it is 2 marks. Or maybe they can even say it's 3 marks also. Then afterwards, they say, maybe they give you 1 eval to make your life to be easy. That's what they usually do, because factorizing is a pain. They give you this, and then they say, find the other 2 evals. And then they give you 2 marks. Then they say, find the EVEX. You find them. By finding the EVEX, they can easily say, that's about 5 or 6 marks. And after finding your EVEX, they speak about invertible matrix T. They can say that's 2 marks. Then they say, find your D, and then hence find your trajectories. Maybe they give this 7 marks or even 9 marks. So the way we say 7 here. So the way they give marks to these questions is very odd. Very odd, but there's plenty of marks to be backed when you do diagonalization. So make sure you are able to get most of these steps right. And in the paper, you are guaranteed you have 15 plus marks already if you can get done this. If you are given matrix A, it's an advantage. But if they give you vector V, you need to extract your A and then carry on as you would, as if you were given the matrix A. So I'll share the solution the solution which we made now in the group. And then we can always have a chat, and otherwise all the best. Maybe we might decide later to say, you know what, let's have another quickie. There's a question of interest. But for now, let's call it. Yes, you can.
So when you found your diagonal matrix, you took the theory that we already know that the diagonals are our eigenvalues, right? But then in class, there's a formula that we are we were taught to use. So if I use this shortcut, will that cause me marks? Like, will that cause me to lose marks?
So my answer to that is twofold, which is, let me stop from reading mode. So my answer is twofold. So we all know that our diagonal matrix will have the eigenvalues. But now, how you position them is what matters. So in class, they gave you a formula. Let me see if I remember. I think it is D, it is T, A, and then T inverse. Yes. Another person can write it as T inverse A and then T. Whatever it is, it's something like this.
Yes.
So with this formula, after multiplying your T, its inverse A and T, you would be able to find D. So what the formula does, it helps you with positioning your eigenvalues depending on how you constructed your T. So if you look at, for example, for the paper for 2016, they say, find D, and then they say, but do not multiply.
Oh.
Multiply. So here's my advice. In the exam, you know, because you are also trying to fight the edge and you are fighting time. If you cannot afford looking at time to multiply 3 by 3 matrices, make sure you position your eigen values very well here. You will get marks. If they say do not multiply, you happen to be very lucky. But in case they do not say anything, looking at time, you are trying to solve ultimately for your trajectories. So which means you need the D, not how you got to the D. So I think it depends on the question. If you can see you are really pressed by time, my advice is do not multiply. If you feel like, you know, I have an extra 15 minutes and I can show the lecturer that I can multiply T with A and then multiply by the inverse, then for sure go for it. But I pray you are given just like your, I think it's 2016 or 2018. They say do not multiply, meaning you need to know how to position your matrix the same way we did in this page here. And say NB at the top. Does this answer your question?
Yes, it does. Thank you.
Okay, no problem. So you guys should make sure you know how to do these diagonalization problems. Really, they are easy. Get your matrix A and then you give it a shot. For the same question, question A, you use the same principles. Extract your matrix A and then take it from there. Believe me, it is very easy. So if there's no further questions, let's call it a day. If I come across an interesting problem, maybe we can say, you know what, let's have a quickie and see what's going on. So if you are happy, please give me your thumbs up and then you can clap your hands. If you are not happy, you can put your sad face there and I'm gonna be happy also. Okay, so I'll share the solution in the group and then you can have a tour and make sure you are able to do these questions. So let's pause the recording and then if there's an interesting question, please share and then maybe if we get time, we can